Hello everyone, thank you for coming. My name is Vittorio Romeo. I work at Bloomberg in the London office, and today I'm going to talk to you about zero-allocation and type-eraser features. I apologize for using a laser pointer in the recording. I had my laptop with my virtual fancy laser pointer, but my laptop decided to die right the night before my talk, which is very convenient. I'm going to wait for people to come in. All right, let's try this again. Hello everyone, my name is Vittorio. I work at Bloomberg in the London office. Today I'm going to talk to you about zero-allocation and no type-eraser features. Again, I would like to apologize for using a laser pointer. I had proper software, but my laptop died, so Felix saved my presentation with his laptop. Thank you, Felix. And what we're going to talk about today is building chains of asynchronous computations. And if you are familiar with SED future, which I assume you at least know what it is, then imagine composing multiple SED futures instances together. And we want to achieve this without type erasure or dynamic allocation, and in order to do that, we will use many templates. So disclaimer, this talk is full of C++17 code and fancy template stuff. I'm not expecting you to understand all the details, but I think it's useful to see a lot of code to understand how you can actually implement this and how it works. I'll try my best to explain, and feel free to stop me at any time and ask questions. So this is a sneak peek of what we're going to have at the end. So we're going to have something like a graph, which represents an asynchronous graph of computations. A leaf is basically a node that stores any particular action. In this case, the first node is simply going to return a string hello, and then we can attach a continuation with .then, get the string returned from the first node, and then append world to it. And this is a graph that, when invoked, returns hello world as a string. Now, the cool thing about this is that you can see I'm using auto here, so the type is being deduced, and the type is not something like SED future, but it's this giant template thing that encodes the entire information about the future graph as part of the type system. So as you can see here, the first leaf over here is something that takes nothing, so it takes void as an input, and has the lambda as its execution. And the second one is a leaf that takes a string and then has another lambda as its execution. And they are composed together by this node seq here, which stands for sequential, which means that after the first node is completed, we will execute the second one. And this is all part of the type. Another example, maybe you want to do something a little bit more complicated. We want to have two GET requests from websites, maybe a picture of a cat, a picture of a dog. And we want to do them in parallel, so we can combine them by using this all node syntax over here. And then after we get both payloads, we can combine them by attaching a continuation that uses a tuple of the two payloads. And inside here, we can do something with the data. And again, this whole thing is encoded in the type system. We have a sequential node that contains an all node as its first one, and the all node contains two computations. And then after this is done, we will execute this other node over here that takes the tuple of the results and executes this other lambda. Make sense so far? Okay. So let's try to understand why I'm doing this and what we have today in the standard. So today we have SED future and SED async, which were introduced in C++11. And what they do, they allow you to basically run things asynchronously and store the results into some eventual future. So as an example here, I can call SED async and tell my library that I want it to be run asynchronously, so in a separate thread. And inside this async call, I can provide an action that will be executed on a different thread. In this case, I'm just waiting for 100 milliseconds and printing out world. Then I'm assigning this to a variable, and then I'm printing out hello. So this will be executed first, then at the end of the scope, the destructor of this thing will be called. It will block until the future is completed, and then it will print out world for me. So that's what we have today in the standard. And there are many problems with this. I'm not going to go in depth into that, but for starters, this always blocks and can be problematic, and also there is no way of composing these things properly. I cannot attach a dot then continuation or have a when all then do something. You have to write that yourself. Also, all of these examples can be run on OneBox, which is an online compiler, so you can get the slides afterwards and play around with them if you want to. So future and async work really well when you want to model some tasks that run in parallel and in a very simple way. So maybe you have F0, F1, F2, you just want to run them in parallel, and then when they are all done, you want to do something else. So in this case, what you do is simply use async to spawn your computations, and they will return some futures. So there's a future F0, futures F1, and F2. And then when these variables go out of scope, they will block until the computation is done. So if you imagine you have something in the middle here, you do your computations, and then when you reach the end, all of these three things will be done in parallel. So it's an easy way to spawn actions. However, the problem is when you have a graph that has some dependencies and some more complicated control flow, it's really hard to represent it by using a CD async and a CD future. As an example, maybe you want to start with an action F0. When this is done, in parallel, you want to spawn F1, F2, and F3. And then when these three are done, you want to spawn F4, and then at the same time also F5. So this kind of very complicated graph is hard to represent with those abstractions because they do not provide any way of attaching continuations or of representing dependency chains. As an example, if you want to do something really simple like execute F0 and then execute F1, so this is basically this graph over here, what you may want to do if you want to have that kind of asynchronicity for both nodes is spawn an action with async that does the first action, and then when the first action is done, spawn another one with async that does the second action. So this is obviously a toy example because you could simply write stdc out hello world, but this is equivalent to the idea of executing something, and when that thing is done, then you execute something else. And this is the way you implement that kind of sequential composition by using a CD future and a CD async, which as you can see is not really great. Also, you might want sometimes to collect multiple features into a single one and then wait on the single one to do something else later. So you might want to spawn A0, A1, and A2 in parallel, and when they're all done, you will get a future that contains all the results, and then attach some continuation B0 and continue with that. So the way you can do it, as a very, very, very rough example, there are better ways of doing this, even with the standard library, is something like you spawn the three tasks in parallel, then you wait for all of them to be completed, and when they're all completed over here, you spawn the other one by using async, and you might want to pass results downstream from the first three tasks. Again, this can be done better in a better way, both in terms of performance and readability, but the point is that there is nothing in the standard library that lets you express when all AX features are complete, then execute B0. I want to express something conceptually simple, and I have to go very low level and build up my synchronization myself, which kind of defeats the purpose of futures. So what we want is some sort of intuitive abstractions that we can use to represent these dependency chains without having to build them ourselves. Boost Future has some of them, and also there is an attempt to standardize them in a CD experimental future, and is part of the extensions for concurrency TS. I'm not sure about the state of that TS. And if you were interested in this kind of extensions, Anthony Williams had a very good talk at ACCU 2017 that explains all of them, and also more stuff, including some parallelism TS stuff and coroutines. So both the Boost Future continuations and the one that are proposed for the standard kind of look like this. So you can say something like boost async, launch this asynchronous action, dot then, some lambda that takes the future as an argument, print out world. So in this case, what will happen is this first action will be executed on a thread, and then when this is done, this other action will be executed, passing the parent future as an argument. So if the parent future returns some value, or through an exception, you can obtain the value or the exception inside the body of this lambda by looking at the argument. Make sense? Similarly, you can have this boost when all abstraction that says, when all these futures are complete, then do something else. So the idea here is that when all takes a varying number of futures and returns a new future that will be fulfilled when all the past arguments are fulfilled. So in this case, when all of these three are done, then this is considered complete, and the dot then will be executed, and B0 will be printed out. So abstractions like then, when all, and when any allow us to intuitively describe these operations. And what they do, they always return a future that can be composed further. So in this case, we can say that the signature of then, for example, in the Boost library, but also in the proposed extensions for the standard library, takes some function and returns a future of the result of that function. Or the when all function takes a bunch of futures and returns a future with an STD tuple of those that you pass as an input. So as you can see, we get in some kind of function or futures, and we get back another instance of future. This allows us to compose them, so we can change the result of when all with another when all, or with a dot then, or whatever you want. And this is why we return future all the time. So as you can see from this example, if you have a future of int a and a future of int b, they have the same type, but b can also represent a continuation attached to a. So in this case, I'm saying that b is a dot then something in my lambda, and even though there is a different shape for the graph, so it's two nodes, the type is always the same. This implies that under the hood there's some type erasure going on, because the shape of the graph is not reflected in the type system. So if the type is the same, then internally there is some type erasure that hides the actual shape of the graph that's being executed asynchronously. Also, future, both Boost Future and STD Future, use dynamic allocation to keep track of the share state. So the place where the result value is placed into, or the eventual exception is created in, is usually a share state stored on the heap that the future and the promise can reach in order to produce the value and retrieve the value. And this is often not a problem because you use futures in the context of I/O operations or internet operations like networking. So the cost of the dynamic allocation and the share state is usually small compared to your workload. But for other applications, such as scheduling work on a GPU, or maybe scheduling work on a thread pool that is very fast, this kind of overhead can have an impact and can lead people to avoid using abstractions and write their own synchronization code, which is unfortunate for the people who have to read the code. So can we avoid the overhead of type erasure and dynamic allocation, and is it worth it? And this is what I'm trying to explore with this talk. Any questions so far? Okay. So I'm trying to find an alternative design that avoids both type erasure and dynamic allocation. The reason why we need type erasure in the first place is because the way features are composed changes depending on runtime control flow, or rather can change depending on runtime control flow. So you could have a node, then you have an if statement that reads keyboard input, and then depending on the input that the user gave you, it can attach a .then or a when all or something different. So you don't know the shape of the graph at compile time, you don't know what kind of computation you'll have, so you need to type erase to allow this kind of composition to happen at runtime. But if the shape of the future graph is known at compile time, so if you know in advance how your computation graph looks when you're gonna fork, when you're gonna join, then we don't need this. We can actually encode the shape as part of the type system. And this is what we've seen in the first slides of this talk. If we know that we're gonna add a.b.c, then we can represent that as a sequence in the type system, and the compiler knows about the shape of the graph. So here's an example of how this can work. Imagine that we have this leaf class over here, and it's a template class. I'm using C++17 class template argument deduction here to avoid providing template parameters over here. And what the leaf class does, it's templatized over an action, so the type of a lambda, and its constructor takes the lambda by forwarding reference and stores it inside the leaf. So in this case, we're asking the compiler to deduce this f template parameter by whatever we pass in the constructor. So we have a leaf f0 that is built from this lambda over here, and then we have some type f1 that is built by attaching another computation to the first leaf. So the first one is created via this constructor, and the second one, as you can see here, is a member function of leaf called then. It takes an arbitrary lambda or function, and then it returns a sequential node that contains information about the first node and the second node as part of the type. So everything we're doing in terms of the future graph composition is represented as part of the type system. The type of f0 is a leaf of some lambda over here, and the type of f1 is sequential of a leaf of that lambda and a leaf of another lambda. So all information about the graph is available at compile time. So similarly, you can do this with whenAll. In this case, whenAll is again a template function. It takes any number of lambdas, functions, whatever you want, and it returns some f0. And in this case, what we return from whenAll is a new type of node called parallel, which contains all the information about the leaves as part of the type system. So we're saying when I invoke whenAll with a bunch of template arguments, then return a parallel node that contains that same template arguments as part of the type system so that we can use them later. In this case, the type of f1 is a sequential node, because we have a .then, of a parallel node of 3 leaves, so leaf 0, leaf 1, leaf 2, and then the second node is a leaf to lambda 3, which is the one we're going to invoke on the then continuation. Make sense so far? Okay. So this is the way we can avoid type erasure, basically by storing everything inside the type, using auto on the color side to deduce it, and forcing the user to have the shape of the graph known at compile time. So we lose the runtime flexibility, but we also gain the ability of doing this without having to type arrays or futures. The other issue that might be a performance problem is dynamic allocation. So future of T, both in Boost and STD, always uses dynamic allocation in order to provide a shared state for the eventual resultant exception and any extra synchronization state that needs to be used for whenAll, for example. So the way it works is kind of like this. So you have a promise, which is an abstraction that produces a value of type T, and you can retrieve a future from the promise that will eventually be the consumer of the value produced by the promise. So the promise is what produces the value, the future is how you consume it. And they both refer to a shared state, which is usually a shared pointer of some data. And you can imagine this shared state containing a reference counter that keeps track of how many futures are looking at the same promise, and maybe a variant of a value or exception that you can use to retrieve the eventual result of the computation. So this is the way it works very roughly in standard library and Boost. So the reason why we need the shared state is because the promise and the future are separated, and since they are separated and they need to refer to the same thing, this state over here needs to be kept alive until both of them are dead. So it needs some way of reference counting or shared ownership. So an alternative that I propose is, since we know the entire shape of the final graph and we have everything in the type system, why don't we just store the state in place inside the final graph object? And this adds another restriction to our user, which is the graph object must be kept alive until the execution is completed, because the execution depends on the state contained inside the graph object. So what I'm proposing, imagine that this graph over here is just a variable in your int main, is auto f0 equals a dot then b. Now, if there is some state between a and b that needs to be shared, that same state is going to be stored inside that f variable on the stack. So the share state is part of the object, and it doesn't require any allocation. However, it forces the f future object to be kept alive until everything is completed. This can get arbitrarily complicated because we have everything in the type system and we can compose stuff. So as an example, if we want to have the similar design for the parallel node, which if you remember executes all of its children in parallel, then we need some kind of counter to keep track of how many things are remaining in order to proceed. And we can store that on the stack inside the parallel node. So the parallel node will contain an atomic counter which tells us how many computations must be completed. And then it will also contain the leaves, which will contain their own states. So all of this is like a very big object on the stack with a large size that contains all the required state to execute this graph asynchronously. And the idea here is that we schedule the first leaf, the second leaf. When they are done, they will decrement the counter, and the last one to decrement the counter will trigger the continuation on the potential next node of the graph. Another example, maybe you have when all of when any of A and B, then C, then D, then you can imagine you have something like this. The innermost node is over here. You will have a state that keeps track of whether it's done or not, because it's just when any, so we care about the first one to finish. Then when all will have a state with the remaining computations to be executed in parallel, which is this one and this one. And then when this is done, the sequential node will execute the final leaf over here. So this kind of code over here will produce a big template type that has all of the stuff, and it's large in size because it contains all the share state that's required for the continuations. And imagine now, like this is what I meant by having to keep the object alive until execution is completed. So if the scheduler over here where we're going to execute our graph is asynchronous, so maybe just launches F on a thread pool or on a separate thread, then there is no guarantee that F will be alive for some time in the future after we call execute, because this might be a non-blocking call. So in order to make sure that the share state between all these nodes is kept alive and is valid, we need to guarantee that the F object is kept alive until execution is completed. And if that is asynchronous, we need to know when it finishes by attaching some kind of continuation and then blocking on the caller side. This is because the share state is not shared anymore and actually exists in place inside F. It's not a share pointer on the heap anymore. Make sense? Felix? Yeah?
Question. Is it possible to provide an execution on different executors? So it's where you start the execution in the background, but then you at the end will update the GUI, which you have to do in the main loop.
So the question is it possible to provide multiple executors for the same graph, basically? Yeah. Not in the current version of the library. I was asked this in Aspen as well, and I think it's required. So right now what I'm doing is passing the function to a scheduler, but what could happen is that I could store a scheduler with every node, and then that would work. So it requires a little bit of changing, but it's definitely possible. So recap before we dive into more code. Type erasure will be avoided by encoding the entire graph as part of the type system, and the restriction here is that we need to know the shape of the graph at compile time. And dynamic allocation will be avoided by storing whatever the share state is in place inside the graph object. And the restriction here is that the final graph object must outlive the execution of its nodes. So if you cannot guarantee that these two points are fulfilled, then this is not for you. You might want to use SD future or boost future. This is for this particular use case. Yes?
One question. Does this mean that all the memory allocated for all the transitions is kept alive inside the graph?
So the question is, does it mean that all the memory allocated for the transition is kept alive inside the graph? Everything that's required for the synchronization, for example, a counter for the when all node and stuff like that, is going to be part of the data members of the graph in place. So there is no allocation unless you want to allocate something. It's part of the graph object itself. Does that answer the question?
Yeah. I mean, so if I have every transition occupies 1 kilobyte and I have 100 of them, I have 100 kilobytes occupied.
Yes, exactly. So if you have 100 transitions, all of them require 1 kilobyte. The final size of the graph object will be 100 kilobytes. There are ways around that. If that's too big, you can type erase at particular points in time, and then you can do that. Okay, so this is what we're going to see, and obviously we don't have time for everything here. This was originally a 1 hour and 30 talk, but I want to go through the leaf node, the sequential node, possibly the all node, and then show you some benchmarks against Boost Future to see what kind of benefit we get. So the first thing to define is some sort of concept for our nodes. If you're not familiar with the word concept in the context of C++, a concept is an interface that must be implemented by something, and in this case, the interface is validated at compile time. So if a class has this execute member function that takes a scheduler as the first argument and a continuation as the second argument, then it fulfills the node concept. In this case, what we're asking is that all the node types must expose the following member function, which will execute the store computation through the scheduler, and the scheduler over here might spawn a new thread or be a thread pool or some GPU scheduler, and then it will asynchronously continue execution via this then function over here. So as you can see, there is no propagation of return values. This will be added later. I'm trying to keep it simple for now. And if you have trouble imagining what scheduler might be, just imagine it's SED thread detach. So imagine that the scheduler, every time you invoke the scheduler with F, it just spawns a new thread for F and runs it in the background. That's the most simple scheduler we can think of. And as you can see, execute is L-value ref qualified over here, which means that the node must be kept alive. You cannot call this on a temporary node because it wouldn't make sense for asynchronous schedulers. So the first node we're going to implement is the leaf node. What it does is simply wraps an action and just fulfills the node concept. So it's just a very small building block for a composition. And in this case, it will expose execute, but it won't make use of the scheduler unless you're explicit about it, because since it's a single action, it doesn't have any inherent parallelism. We can just execute it on the main thread. So in this case, this is an example usage. You just create a leaf with a lambda, and then you call l.execute with your scheduler and your continuation. And what will happen is that this action will be executed, and when this is done, it will execute this other action, so it will print out hello world. So this is a very convoluted way of printing out hello world, but it lends itself to composition with the other abstractions. As I said before, the template parameters here are deduced thanks to C++17's class template argument deduction. If you don't know about that feature, it's basically, sorry, I'm going to have some slides later, but it basically allows you to avoid specifying the template parameters here, and they will be deduced from the constructor call. And also, the continuation is provided as a callback over here, because we want to avoid unnecessary blocking, especially in the case when we have functions like when any, as we want to continue as soon as possible when any of the futures are done. This is the entire implementation of leaf in C++17. So what we do is we templatize over our action type. We inherit from it, because if the action type is an empty lambda, we don't want to pay any extra cost for storage, so we can use the empty base optimization over here. And if you don't know what that is, it means that if you derive from something, instead of storing it as a data member, if the thing is empty, then it doesn't take extra space. Yeah, C++ is weird. And then we expose the execute method to fulfill the node concept. We take the scheduler, but we don't care about it. We take the continuation, and what we do is we invoke ourselves, because remember, we also are a lambda, so we execute our action, and then we invoke the continuation. So in this case, this will print out hello, and this will print out world. As you can see, there is no parallelism here. It's all sequential. It's all very simple. This is just a way of providing a building block for composition. So this is how it works, how the deduction works for the template parameters. If you never used 17 before, this is a very, very useful feature. So if you have some lambda and you create the leaf over here, the compiler will see, oh, you didn't provide any template arguments. Can I deduce them somehow from the constructor? Then it will look at the constructor and it will see, oh, you're taking an f in your template in your constructor arguments, and it's the same f that the leaf is supposed to have as a template parameter. So I can deduce this f from the f over here. So what the compiler rewrites after seeing this is something like this. The compiler just puts this decal type for you over here and says, I'm going to deduce f to whatever the type of some lambda is. So this is being done for you. And this works with every type in C++17, so stuff like vector, std array, std function. You don't have to specify the function type yourself. You can just let the compiler deduce it. So the leaf node on its own is not really useful, so let's look at the sequential node next. So the sequential node takes two nodes A and B as input. It executes A and then B. Remember that this can mean anything, because if A is a when all node, it needs to wait until everything is done and then execute B. If A is a when any node, it needs to wait until any of them is done and then execute B. So we need to have this sequential node generic enough to work with any type of nodes without unnecessary blocking. So in this case, imagine we have two leaves, hello and world, and then we create a sequential node by moving the first leaf in and the second leaf in. Then we call execute with our scheduler, and then we have a continuation that prints out an exclamation mark. And this will just sequentially execute hello, world, and an exclamation mark. And it will print out what you expect. How does it work? So this is the entire sequential node implementation. We have a very similar strategy over here. We have two functions, A and B. In this case, these are our nodes. So node A and node B. We derive from them to allow the empty base optimization to kick in. And we have a constructor that allows us to move A and B into our sequential node. And then we expose the execute function to fulfill the node concept. It will take a scheduler and a continuation. And what we're going to do is we're going to execute A first on our scheduler, and then as the continuation of the execution of A, we're going to provide this lambda over here that executes B when it's invoked. So we're basically saying, execute A on the scheduler, and whenever this thing is done, which might be sometime in the future if the scheduler is asynchronous, then please execute this lambda over here, which captures the relative information. It captures the then continuation by value, as the sequential node might have been on out of scope. Then execute B on the same scheduler with the continuation that was originally passed to the sequential node. So this is the way we tie everything together. Make sense? Okay. And yeah, so this is an explanation. A is immediately executed. The execution of B is passed as the then argument to A execute. So we're packaging up the execution of B and passing it to the then argument of A. And this kind of thing, compared to a sequential A execute and B execute, allows non-blocking asynchronous composition, because there is no guarantee that A will be executed on the same thread, or that it won't be something special like when any. So again, this is what we had before. Kind of looks like this. The sequential node contains two leaves, and then the first then continuation of the first leaf is attached to this one, and the second one is attached to the final continuation, which is the lambda over here. So this is completely sequential. We propagate the scheduler along, but in this case, no one is making use of the scheduler. It's just being propagated in case someone might need it. So why do we do this? As I mentioned before, this is crucial for nodes that have some inherent parallelism or asynchronicity inside them. Imagine we have a when any node, and the semantics of this node are, I have a bunch of computation, as soon as one of them is done, I want to continue. So we use this kind of asynchronous callback-based continuation, because if this is an any node, and we use a sequential to link it to a leaf node, imagine F2 is the first one to finish. we don't want to wait until all the others are done. We immediately want to continue from F2 to G0, and then the other two can run in the background. So that's the reason we cannot block between A and B. We need to be asynchronous. Any questions so far? Yep.
Why do we need to capture the
So the question is, this, you mean? Okay. The question is, why do you need to capture this in the lambda? Because B is a base class. So it's stored as a base class of this, right? So when we access it, we're actually saying static cast B of this to get to that member. So this needs to be captured inside lambda. Okay. Let me check the time. Okay. 15. Yep.
What if I want to stop F0 and F1 when the F2 is?
Well, I accept pull requests. So there are many ways you can do this. I haven't implemented any. Theoretically, you could detect inside the bodies of your actions if there is some kind of cancellation token or cancellation flag. That's one way of doing it, but it requires the user code to be polluted by it. There probably are better ways, maybe Felix has.
So I think it's the easiest thing is if F0 and F1 did not start so far. I know that's pretty easy to implement. So if any of them is not started, you can stop or prohibit the starting. Otherwise, it's not good to interrupt running thread.
So that's an important thing. Another thing is, like, if you're running F0 and F1 and you don't really care, as long as the important thing is not continuing from them. Like, imagine they had a chain of things, F0, then A, B, C. Then just run F0, then stop the chain as soon as possible. That's another thing you can do. I'm running a little bit low on time. I'm just going to show this and the benchmarks. So this is the all node, and it will be the first one to make use of the scheduler. This will be a little bit more interesting. It takes an arbitrary number of nodes, Fs, as input. It executes them in parallel, and the execution of the node is completed when all the children are completed. So you can write something like this. You can say, I have an all node called graph, which is composed of 3 leaves, A0, A1, and A2. Then I'm going to execute my graph with some scheduler, and my continuation will be B0. And note this very production-ready sleep over here that prevents the graph from going out of scope, because we don't know when this will be completed, so it has to be kept alive because the share state it's in place inside the graph. So there are ways of making this nice and deterministic, but for this example, just sleeping will do. So this is what it looks like. We have this all node. It contains the 3 leaves. And it has some share state inside it, which is an atomic counter keeping track of how many things are still need to be scheduled. Sorry, still need to be done. In this case, we start at 3. So then we run all the leaves in parallel, and as soon as every leaf is done, we decrement the atomic counter from the continuation of the leaf. When the atomic counter reaches 0, then we can invoke our continuation B0 over here. So independently of the order, every leaf will decrement the atomic counter. Eventually, the last one will finish and will execute B0 for us. So basically, this is what I just said. The atomic counter keeps track of how many nodes need to complete their execution. When it reaches 0, the then continuation of the all node is executed. And every node, as we pass as an input, decrements the counter upon completion. And since the nodes can be executed on separate threads, this object needs to be kept alive, so this is why we have the sleep. And we can see a more robust solution later in the slides. So this is what it looks like. We have this all variety class template thing. It takes a bunch of nodes and derives from all of them to make use of the EVO. And not only for that, but also because it's easy to work with the FS as a pack when doing expansion. It contains an atomic int of how many things are left, and it just moves everything into the base classes. So this is the execute method. First, it will atomically store how many things are left into our counter. In this case, we can retrieve the number of things in a variadic pack by using the size of ... operator, which in our example is 3. So we'll just store 3 inside the left thing. And then, I'm sorry, I have this fold expression over here. So this entire thing is a fold expression. And what I'm folding on is the fs pack over here. So what's happening is that I'm asking the compiler to copy-paste this entire block of code n times for each function over here, basically switching this one between all the base classes. And this is a C++17 feature, and as you can see I have a comma here and a ... which means that I'm basically asking the compiler to fold over the comma operator and copy-paste this block of code as needed. So the idea is that we will call this with F0, F1, and F2, and we basically are scheduling this lambda that captures all the required state, and F is the current computation, so it can be F0, F1, F2 if we are all of them. And we're gonna execute the current computation passing the scheduler, and the continuation of what we're executing is a decrement on the counter, which checks if we are the last one to decrement it, and if we are the last one to decrement it, then we will invoke the then continuation of the all node. So I'm going to try to break this down a little bit. So this entire thing is a fold expression over the comma operator. And in short, it means let's schedule the execution of every f in fs. And as part of the continuation of every f, we will decrement the atomic counter, and the last f to decrement the counter will also be responsible for executing the then continuation of the all node. So as you can see here, this is what happens. We are decrementing the counter, and if we are the last one, because fetch sub returns the previous value. So if the previous value was 1, we are the last one, then we're going to invoke the then continuation of the original node. And we are scheduling all of this. So this means that if the scheduler is simply creating new threads, we'll create a thread for every single computation inside the all node. So this is an example expansion for 2 hypothetical A and B nodes. In this case, our fs pack contains 2 types A and B. So that will expand to 2, and then the fold expression will have this expansion over here over a comma. The first one will capture A, the second one will capture B, and the body will be identical, just that we're executing A and B in the other one. So the compiler is generating this for us thanks to the fold expression. Yes?
Probably it should be equal operator instead of the same.
Where, sorry? This is a double equals, it's just the font being weird. So it's equality, yeah. Yeah.
The final implementation will take care of the force sharing of the shared account.
Yes, that's a very good question. Do I take care of false sharing? Yes, every function is aligned on a cache boundary. So I tried to be as I benchmarked it. It doesn't have a huge impact though. I think it might have a huge impact when it's like in a tied loop or something like that. But you can do that. Okay. So what we have so far is leaf, sequential node, all, and this allows us to already model arbitrary fork and join computation graphs. So as an example, if we have this thing over here where we have A0, B0, B1, and B2 in parallel, and then C0, we can write it like this. It's terrible syntax. So we can have A0, and then we attach an all continuation with B0, B1, and B2, and then we attach a continuation with C0. So I'm running out of time. This is just meant to be give you the idea of how this works. But the next thing to do is propagate the return values, which kind of changes how this works a little bit. We have this new input parameter on execute methods, and we pass it forward on every node. Yeah, it's not simple. The other thing we can do is get rid of the sleep over here, and what we do is basically use a latch, which is a counter that allows us to block until the counter reaches 0, and we provide an abstraction that says we want to execute this graph synchronously, so we have a latch, we execute the graph, and we attach a countdown on the latch as the continuation, and wait on the latch. So we're saying execute this graph however you want. When you are done, decrement the latch, and when the latch is 0, just unblock it. So this allows us to prevent the slip and have deterministic lifetime of the graph. And finally, some other things we can do is improve the syntax. We can have a simple continuation-based syntax by allowing .then chaining, for example. And this is very simple. We just add a then member function to every node type, and what it will do, it will simply return a sequence of ourselves, like because we are the parent node, and then whatever we pass as an argument. And here I'm also doing some wrapping. If you pass a lambda, so you don't have to say leaf, it will automatically be wrapped into a leaf for you. And now you can say something a little bit nicer. You can say start by this, then do all of this, and then do this other thing. So it's a little bit of a more sane syntax. Finally, the any node is quite complicated. You need some sort of reference counting to make sure everything works properly. So you can read that yourself or see other versions of this talk. And this is the part I want to show you. So what do we gain from this? Is it worth it? So here's how you read this graph. First of all, I'm benchmarking as boost future because I couldn't find any implementation of the standard library extensions. So this is boost future. And the way you read this is basically what I'm doing is running a computation 100,000 times in a tight loop. And this computation can take different amount of times. And what I'm trying to measure is, if the computation is very short, like it's a very small computation, how long does it take to run the entire loop? Or if the computation is very long, how long does it take to run the entire loop? So what I want to see is, how short does the computation have to be for me to benefit from the lack of type erasure and dynamic allocation? Because if my computation takes 2 seconds, then I'm not going to care about these optimizations, right? But if my computation is very short, then they can have an impact on it. As an example, this is just running a single node. So a very simple single node, we just run it. And boost future, as you can see, even if the computation takes 0 milliseconds, adds some overhead just required to set up the dynamic allocation and whatever threading it needs to do and stuff like that. In my case, instead, up until computations of like 1 milliseconds, you can see a benefit from avoiding all that extra dynamic allocation and type erasure. So the compiler is more liberal with its optimization, it's free to inline more stuff, and we don't need to allocate or type erase anything. If we have a simple chain like A.then B.then C, then my model wins by a lot, because since this is completely sequential and it's part of the type system, it can be squashed into a single sequential set of instructions. So as you can see, there is a gap between boost future and my model up until like 1 millisecond when it doesn't really matter anymore. And this gets worse when the chain is longer. Again, since everything is available at compile time, in my model, it doesn't matter how long the chain is. If it's linear, I'm just going to squash it and collapse it into a single node. Now, I try to be a little bit more fair here, because I can do this because I have all the information at compile time, while boost future is required by design to allocate and schedule every single node on its own, because it doesn't know what the continuation will be. But it also provides this deferred launch thing in its boost async that says, I'm going to run it on the same thread without scheduling any extra, without spawning any extra thread, any extra thing. However, even by doing that, which means running it on the same thread, there still is some overhead due to the type erasure and dynamic allocation, which, depending on how long the chain is, might still be significant up to something like 1 millisecond. So as you can see, even when the compiler is not forced to schedule something, even when it's on the same thread, we still have some overhead due to the dynamic allocation and type erasure. Then we can do a little bit of more complicated things, like an all with a .then, and there is always a gap around 1 milliseconds. And any node as well, we have a similar gap. And then if we start doing things in a more complicated manner, like this one, then using a thread pool compared to simply scheduling spawning a new thread starts being beneficial. So in this case, I'm using my library, which is called Horizonte, with a thread pool. I'm using my library with the normal scheduler and boost future. And as you can see, the more complicated the graph is, the more degree of parallelism you have, the more it's beneficial to use a thread pool. And again, I think that the cutoff point for all these kind of computations is 1 millisecond. So if you have something that takes more than 1 millisecond and you do it in a tile loop, then you won't really get much benefit out of it. But if you're just trying to have nice syntax to basically schedule things in parallel, which are very short-lived, like around 0.1 milliseconds or below that, then doing this over boost future is fine. So that's it. I have 1 more minute. You can find the library here on my GitHub page. And my point here is that you can apply the idea of expression templates, which is storing things into the type system, to pretty much anything. Also, I found sanitizers invaluable, especially thread sanitizer, to find out very weird concurrency bugs and use after free bugs and stuff like that. So thread sanitizer was a lifesaver when implementing this. And C++17 features like fold expressions and class template argument deduction really make this possible. You can do this in 14, in 11 even, but the code is going to be really ugly and full of boilerplate. So 17 simplifies things a lot. And thank you for coming. If you want to find the library, you can find it over here, and the slides are available over here. And feel free to contact me or find me afterwards. Thanks.